proteins / amino acids. Do you remember back was that last week? Organics, when I introduced organics with the carbs, proteins, and lipids were in that list. So we're going to cover those other two categories today. And those are your objectives, okay? Proteins are complexes made of amino acids, okay? And you've heard of amino acids a lot, probably. And they're long chains. They can compose up to the 20 different amino acids. As of right now, there's 20 amino acids, but that could change probably at any time. They consist of carbon, oxygen, hydrogen, and nitrogen. So there we have a difference now. A few have sulfur, but we're not really going to get into any of that. Just made a notation of it, okay? And almost all of them are synthesized in the liver. In your textbook, it says there are 8 essential amino acids, but actually there's probably more than that. I think about half are essential and half are not. And what does essential mean? And expound on that. Well, what's the difference between an essential amino acid and a non-essential amino acid? We need them all. Yes, essential is not. So it is essential that we eat them. And we said with carbs, they are not essential, so we don't have to eat carbs, but we need to eat proteins to get the half of the amino acids that are not going to be produced in our body. And some of those that we ingest, when they're broken down, create another one. So it just depends on your reference, how many they're going to consider essential. Your textbook says 8. I'm not going to drill you on those, but just realize we do have to ingest quite a few of them. This is their main configuration. R is a radical group, meaning it can be just about anything else. Okay, so we're not too concerned about the R. That's what distinguishes one from another. But they all will have this central carbon with a hydrogen attached to it. The R is attached to it. That is different. And on each side of it, the carbon, we have an amine group, which is composed of the nitrogen, has 3 bonds, so it has 2 hydrogens along with the carbon binding, and a carboxyl group, which is C, double O, oxygen, single bond OH. That is the basic structure. So I drew it out with the double bond in here so you can kind of see how it is. This is the simplest one because this would be a hydrogen for glycine. Can't get any more simple than that. And then they just build from that. So the rest of them won't have a hydrogen, they'll have something else, which can get pretty long and complex. They're considered amphoteric. And what I want you to get out of this information is that one end, the amine group, can accept a proton, and the carboxyl group can donate a proton. So hence, the carboxyl can be negative, and the amine can become positively charged. That charge then carries on down here for pH. Okay, an isoelectric point, and I don't expect you to know what every single one is, but realize that is the pH where that particular amino acid will be neutral, meaning it has the NH2 on one side and the COOH on the other. There is no charge going on, it's neutral. But as you change the pH and it goes up, then we're going to be removing a hydrogen, so it has a negative charge. Or if we add a hydrogen and the pH goes down, it becomes positive. We use that characteristic in some of our testing to help us distinguish the elements, okay? Amino acids are linked together in chains, and where they link together is called a peptide bond. And have you heard the term polypeptides? That's what we're talking about. We have multiple attached together with this peptide bond where one amino acid will attach to the other. And it involves the amine and the carboxyl groups attaching to each other. The side of the amino group is called the N-terminal or N-terminus, and the side of the carboxyl is called the C-terminal. And something down the road, we actually call something by name with N or C-terminus, blah, blah, blah. This is showing you just those two parts of the molecule. Here's the carboxyl group, and here is the amino group. And they are going to bond. The H and the C are going to attach. So that means the COOH has to get rid of something, a single bond, so it can bind to the nitrogen. Then amine group has to get rid of something so it can bond to the carboxyl group. They both have to give up something so they can bind together. So here is one amino acid, kind of like our little models last week. Here's the second amino acid, and here is what they're going to lose so that they can bind that carbon to the nitrogen. And what do you see? Water. So in order for them to bind, they have to give up a molecule of water. This picture is not in your textbook. This is about the best picture that I've come up where things are labeled. This is showing you a basic amino acid, and here is a peptide bond where this amino acid has attached to this amino acid. So we lost a water molecule here, and here is another one, another amino acid, and another peptide bond. So this has 4 amino acid with 3 peptide bonds, right? And that's what they start to look like in their sequencing. How they are categorized is based on their structure, how they're put together. We're talking about up to 20 different configurations being attached to each other, so it can get pretty complex. First, a very simple category is how they are attached. The sequence of the amino acids, the order. So think of it as a straight chain, and the different amino acids that are bonded together with this peptide bond. Now, all of them have an R group, and some of those R groups are bigger than others. Those R groups are going to start interacting because they're hanging out to the side. It's going to have to think three-dimensionally. And they're going to interact with each other. How they interact with its neighbor determines the secondary structure. And that's where we start to see a coil. Okay, so think of a straight piece of string. Then think of a ribbon that's been curled, where the two sides are kind of kissing each other, flapping in the wind. Then it gets a little more complex, and this chain will kind of fold back on itself and make a ribbon that you have put in your hand, a ball of it, so to speak, and that's your tertiary structure. And it's very three-dimensional. It's all three-dimensional, but this is like a ball now. Then we can get even more complicated where we get a bunch of polypeptides. Here's one over here, and here's another one, and we start putting them together, and we get a big mass of ribbon that is a bunch of pieces. And you know how hard some of that is to untangle? If you ever had a bunch of chains, say some fine necklaces, stuck in a drawer, and then you pulled them out and tried to get them all apart? They're not connected, but they're really complicated to get apart, to break those interactions. And that would be your quantiary. We are actually going to use these bonds, the peptide bonds, in these different configurations, the secondary, tertiary, and quaternary, break them. And we use different characteristics and different tools in the laboratory to break those bonds up so that we can separate the components, such as heating them or changing their pH, so that's the PI change, or using some kind of force, exposing them to chemicals or UV light can disrupt those bonds. So we use all of those, not all together, but in different parts, depending on what the scientists have researched and figured out the best way to separate some of this. Okay, the function of proteins. They're very, very important. Yes, they are essential for life. They maintain, the biggest thing is they maintain colloidal osmotic pressure in the cells, which is directly related to water distribution. Okay, they're making a lot of water molecules when they're binding together. We need them for structural support. And here's some examples of some proteins which we will, and you have talked about some of these already, but next week we're going to talk about enzymes. They are proteins, and different hormones later in the semester. You've already talked about hemoglobin and antibodies. They are proteins. And here's another little, okay, we're going to talk about a little bit of disorders. Amino acidopathies. These are pathological conditions concerning amino acids. There are over 100 different inborn errors of metabolism. Would you like to know what they are? Do you want me to list all of them? No, I'm not going to. Some of them are pretty rare. But there are a few more common ones that you want to get a little familiar with. And most of them have to do with enzyme deficiency. And you've probably talked to somebody that has an enzyme deficiency. People that are lactose intolerant, they're missing an enzyme to break part of the carbs down, and so it creates problems for them. When something isn't broken down like it's supposed to, that primary state builds up. So that primary state could be toxic or create problems. Or it's not breaking down to the functional portion they need, and that might create problems because they don't have it. So sometimes one or the other. It's because they're having toxicity levels of the before or not enough of the usable function portion of it. And alkaptonuria, anything that ends with urea stands for it's showing up in the urine. Okay, so they're spilling out too much of the product that an enzyme should be breaking down because they have too much of it, so it's spilling out in the urine, and that's where we detect it. And it's a homogenetic acid that is the primary component that does not get broken down, so it builds up in the tissues. Cystinuria is another one that's pretty, I hate to say common. These are not common, but more common than others. And you may have heard of maple syrup urine disease, MSUD. Yeah, the urine actually smells like maple syrup, and that's why it was called that. Has that certain characteristic about maple syrup, real maple syrup, not artificial syrup. and it's a little dark. And PKU, that is probably one of the most common ones. And most of them, with doing some restriction or addition to your diet, you can take care of the problem. If it's a matter of you ingest a component and then you're missing the enzyme that's going to break it down, don't ingest it. Okay? If it's a matter of, well, I need the end product required, then you need to take, like, the enzyme to help break it down. Okay? So it just depends on which one it is, what your treatment will be. But because so many of these are simple to treat and they create devastating results or syndromes in people, the government began doing studies and decided we need to start screening our babies. These are an easy fix. And if we know this baby has it, we can prevent them from having lifelong misery or poor health. For instance, the PKU, just don't eat phenylketouronics. That's all you have to do. It's in a lot of foods. And so part of this government study and then stepping into starting regulations was food has to be labeled. That was a pretty common one. It created mental retardation. So just by not eating certain foods, you can prevent that in your child. And that's, that's an easy fix. So little by little, we started doing baby screens, newborn screens, so that when they're born, we detect certain ones. And they got, PKU was the first one. I actually am old enough, I got to do PKU, and it was an all-day process and very time-consuming, very technique-dependent, and you always prayed and made sure that it worked because if you had to do it again, you had all these babies. We probably did them once every 2 weeks, so we had a lot of babies that you'd have to round up if you had a problem. And because of the time frame, and it's not something that we did very easily and very often, the specimen was a little bit different than a typical blood collection. So we collected blood on paper and let it dry. So to make it standardized, we had a designated hole puncher so that all the holes were punched out the same size and idealistic had the same amount of blood on them. And then we eluted the blood off the paper into saline, and then we tested the liquid. Sounds pretty archaic, but we still do that. As time went on, we came up with more and more of these amino acidopathies that we could measure. And so eventually they didn't want everybody with their hands in them because there was inconsistency. So most states now have one state-operated lab that does all of the births in their state. Now sometimes we lose some people along the way. The at-home births or the people that get discharged early and don't come back or move away, or a lot of times it's due to lack of education. They don't understand the need for it. They don't want their baby stuck because it is kind of painful to watch your brand new baby get stuck. So somebody has to stay on it. Whoever is in charge in certain ways, they have to constantly be on the parents. The physicians are always notified. So it's a pretty big process just to monitor and regulate. As they added more and more tests, and this is an old one. I do have one to show you, but it's not real clear. We collect, and I've got two. So you can kind of look at them and pass them down. On the end, behind this flap, it's paper with circles. Okay, and some of you who've done phlebotomy have seen this or actually done these. Okay, and you get all of the personal information. This is like your record, all these pieces of paper, and you have to write everything about the baby, exact time of birth, and some of the tests you have to wait till their system has cycled. So they generally go 48 hours, maybe 72 hours after birth. Well, there for a while, the insurance was sending everybody home at day 1. I, for one, said, "No, that's too early." They need to keep them 2 days. And so often, this is the only reason they get to stay, is when they hit that 48 hours, which I think that's what they're still using. Is that what they're using, 48 hours? You get that heel stuck, collect that blood, and you're off. Go home, okay?
Is that one of the reasons why you don't get discharged from the hospital?
One of the reasons. Right, right. That's what I was saying. For a while, the insurance kicked in and said, well, a mom can go home at 24 hours. Well, some of them can, but some of us couldn't. And those babies went home and didn't come back. Because you can't, if you do it too early, some of the testing hadn't kicked in yet. Think about the babies born, their GI system is new, and I don't know, a lot of you know, but they have this meconium, and it's the stuff that they have swallowed while they're in utero, and it's real tarry and sticky, and we can't use that for a lot of things. So you have to wait till their GI system cycles, and whatever their diet is going to be it breast milk or a formula, has to go through their system and get cycled, and that's why the 48 hours. To get a good blood detection or deficiency of whatever it is we want to know. That's why we need 48 hours, 48 to 72 hours, 2 to 3 days post-birth. And that is the main entity that has created problems for the early discharge. The policies usually are, you go ahead and collect it, but you tell them they have to come back. Well, you know, if you've got a brand new baby, especially if you're having some problems or you've got 10 kids at home, I'm not going to drag them back out just so you can stick their heel if I don't understand the need for it. So they weren't getting a lot of those returns to have them restocked. So it was much better, cheaper in the long run, if you want to look at the money end of it, to just keep them to 48 hours and get the one specimen that you need. Okay, get up my politics. But we have lots of information on that card, and it gets divvied off. Whoever is the assigning attending physician gets the report, and it's their responsibility to follow up with the parents about the baby if there is a problem. If there is a questionable result, we don't take any chances. We call them back in, and then we will have blood collected to do a bigger test, more qualified test like we do in the laboratory. But this is more like a screen. And I don't know how many they're doing now, probably 20 to 30 different tests off of those few drops of blood. But if you happen to be the one that gets to collect it, and some techs do have to collect this, it's really important that you fill those dots properly. That means all the way full and saturated, so all the way on the back side is soaked with blood. Okay, so if you just get close to that line inside, when they punch it out, they're not going to have the complete amount of blood. Or if you don't let it soak to collect enough to soak it all the way through to the backside, it's going to be Q and S. So that will affect their testing. So it's important that the collection be proper. Well, then we have this piece of paper, and it's got this wet blood on it, and we have to let it air dry, and then it has that little flap over it to protect it after it's dried. I don't know if they still do this, but when I was working, we stuck them in an envelope and mailed them off to state. I think they put them in plastic now, but we just use a regular envelope for a long time. But they're pretty stable. They're dried blood on this piece of paper, really. Yeah, that was a major problem. But all the contact information was there for the physician to get the report, the hospital got the report, the parents got the report, but you know, if it says you need to go see your doctor, some parents didn't take it seriously. So we do have some problems with follow-up. And then your home birth, we might not even know about those. So we still do have patients with amino acidopathies that could have been prevented. Okay, let me have my cards. These were hard to get, so I have to take care of them. I like the little biohazard sticker on here that we put in the mail. But this is a lot of information, and this looks so primitive to what our other testing are, but I don't know if this will ever change. I guess if we ever learn to get a point of care meter that can test all these, it will just do a heel stick in the hospital, but right now we're not. Okay, before we go any further with proteins, I want to back up to methodologies and talk a little bit more about electrophoresis. Anybody remember from methods what electrophoresis is? Yes, everybody does, right? Or separating a molecule into components, or not necessarily even a molecule, just a separation using an electrical current, electro. So we take a specimen in some fashion, and it has to be attached to something, like a paper, like you put your chromatography samples on, a piece of paper. You didn't add any current, you used gravity and the solvent migrating. But you put this paper that you put your specimen on in some kind of well and apply current, positive and negative, so that the current is flowing through this paper where your sample is attached. And it's not just paper, it's a little sophisticated. We use an agarose gel for the most part for basic protein electrophoresis. SPE, serum protein electrophoresis, will be your order, and that's how you'll see it referred to. We are not expected to teach you about electrophoresis, but you need to understand it to help you understand the rest of this protein lecture. Okay, because it's built off of the premise of the electrophoresis. So this is a graph showing you, here's your positive and negative current. Opposites attract. So wherever you put your sample, my negative are going to migrate to that positive, and my positive are going to migrate to the negative. So they're going to start separating. And based on the pH, the amount of current, and the time that you are controlling where they'll stop, how they will separate. Some will go really fast, some will go really slow. And so the scientists have done all the research and find the optimum buffer solution, what pH it needs to be, how much current you need to apply, and for how long. That we control in the laboratory. So we apply a very small amount on a particular medium and follow their instructions. Well, all you have is a piece of paper. You still can't see anything because these guys don't have any color to themselves. After it's finished and you get it nice and dry in some fashion, you'll apply a stain. Okay, and so there is our color metric that we're talking about. So instead of a test tube full of a blue, we'll have stripes of the different parts of the proteins, depending on how we control those parameters. Okay? And then certain stains in certain pH liquid stain certain things. So you could do the same type of migration on two different plates and then stain them in different solutions and see different things. This is a picture of a plate that has, let's see, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 samples on one plate. This is A. These are two samples together. Okay, where it says Beckman is a dividing line. That's another plate over there. So on plate A we have 10, and the positive charge was on this side. and it looks like we have something really big. This is all one person right here. Here's all one person, number 9. And they all have something really big, a lot of one thing that all went to the same place. Okay? And then some of them have a large amount over here somewhere in a little bit different places. Can you see this line right here? Most of them have this. There's a little bitty one here. I don't know if you guys can see it right next to the big one. This plate over here only has 5, but it's got the same components, but it has nothing real big on this side. This is the agarose gel, and I have some samples that I was able to acquire to show you what they look like. Let's see. No, let's just look at this. Okay, that one's only got the report. These are the plates, and agarose gel is on a plastic sheet, like a sheet of Mylar, and it looks like a really, really thin layer of jelly, and you can actually destroy it with your fingernails. And so the serum kind of soaks into that, and then when we apply the current, they flow through that gel. And then after we're finished with it, we put it in the oven, and it dries. Well, it's actually a separate piece from the backing, and you can peel it off. It's like a super thin layer of cellophane paper. It's really fragile. So I covered them up and taped them all on there so hopefully they won't fall apart. And I just kind of listed. We got 8 samples that we applied to a plate. And I just listed some of them. You always have to run controls, just like with all of our other runs. So we usually have a serum that's considered a normal control, and then we'll have an abnormal serum, which means something's in there that's elevated for us to compare our patients to. I have another one that I'll be passing around. But, you know, you can kind of see the stripes. So this is one patient from side to side. We actually applied them about here. So you can see a little bit went this way, and a lot of it went the other side. Okay? But they all separated, and then the stain picked up where the different separations are. This is SPE, serum protein electrophoresis. It is a little complex, but it's not as complex as some of the others. And this is more of a special area that you might get to see, but you would not be doing this as an entry-level tech. Each of these on your protein were categorized, a name, okay? The very big one that everybody seems to have a lot of is albumin. If we put this on a spectrophotometer that moves, we can scan the different parts. Okay, and that's what we have done here. This picture is a picture of a spectrophotometer, and we call it a densitometer. It is measuring the density of the red color here in contrast to each other. So if you added it all up, it is 100%. And if you look at it, and almost everybody looks like this. This is your big peak. A whole big chunk of it is this first peak. Then just a little bit of the second peak, a little bit more of the third peak, close to the same of the fourth peak, and then the last peak. These were all named to begin with, and that's what this next graph is showing you. That big peak is albumin. So over 50%, actually 60%, of a total protein amount is composed of albumin. And we were measuring total protein with our biuret. Okay? We weren't measuring just albumin. We were measuring all of these. Okay? So if I know the total protein grams per deciliter, and I know the percentages of each of these, I can calculate how much grams per deciliter each component is, the 5 major components. And that's kind of what we do with protein electrophoresis. So we expect to see a big percent of albumin, then alpha-1, alpha-2, and they didn't put the 1 and 2 on here, beta, and gamma, because I think that our equipment wasn't real sophisticated at first, and we just came up with alpha, beta, gamma, and then they said, oh, wait, there's 2 of them there, so we separated alpha-1 and alpha-2. The proteins that we are going to talk about all fall under one of these fractions, okay? And it might help you to learn them that way because they kind of act very similar. So half of their name is sort of like we have an alpha-1 something or a beta something. And you learned all about gamma globulins, didn't you? Yes. Immunoglobulins, a whole semester of them. They all fell here under the gamma peak, gamma globulins. So we have albumin. All of the rest of these are considered globulins. Alpha-1 globulins, alpha-2 globulins, beta globulins, gamma globulins. And this chart has identified some of them for you. Here's an alpha-1 antitrypsin, alpha-1 acid glycoprotein, and here is your IgA, M, and G, okay? And they all fall at a certain place in each one of these 5 major fractions of total protein. Okay, so you have albumin, everybody else is globulins, but we have 4 parts, alpha-1, alpha-2, beta, gamma. Okay? This is a normal one. I did label right here. Occasionally we see something right before albumin, and we were really sophisticated. We called it pre-albumin. Okay? And then another generation came along and changed the name. But we used to, if we would see anything right before it, we called it pre-albumin. Okay, based on the electrophoresis, we're going to break them up in those 5 main fractions. We're going to talk about transthyretin. That is your pre-albumin, and I've got a slide on it. Albumin, that was the great big one. And then all the rest are your globulins. So we're going to break it up into 3 parts. The specific proteins. The first 2 are pretty easy. Transthyretin, look at the word. TTR, previously called prealbumin, and that's probably all I'll ever call it. Look in the function here. It binds thyroid hormones and retinol. It is a transport protein. Almost, well, not all, but a big chunk of your proteins are for transportation. Transthyretin. Transport, thyroid, and retinol. The name is built right into it. It's one of the easier ones to remember. What does it do? You know, if I asked you, well, let's break up the word. Trans is always a transport. Most of them are synthesized in the liver. However, this one contains essential amino acids. Because of that, it makes up clinical significance for nutritional status. Somebody put that in everyday words for me. How can I use this element to know nutritional status of someone? Very good, very good. Yes. We use this a lot in our older people, or sometimes when people are really, really sick. We will measure the TTR or the prealbumin, and if they're not eating properly, they're not making enough of it, which is going to affect the thyroid and what it's supposed to be doing, and your vision. Okay, so that's the main thing I want you to get out of TTR. Albumin. is synthesized in the liver. It generally comprises about 60% of the total. Its main function is really transporting, takes everybody here and there. Big bus, I guess you might say, shuttle, which indirectly is to maintain the osmotic pressure in your water. And you have a box in your book that discusses that. This box is talking about hypoalbuminemia, okay? Our albumin is low, so it's less than 60% of our total protein. If you have some reason that you're using a lot of it, it's transporting and maintaining pressure, so you have some condition going on where you're utilizing a lot of it, you're going to use it, and so you're not going to have very much showing up in your circulatory system, like liver disease. Or if you aren't taking it in, diet, or some malabsorption issue. We will increase loss with all of these. Just protein, albumin, is related to a lot of conditions. That's why we have so much of it. So anything that can affect it will give you a reduced amount. And the easiest way to remember it is you're losing or using it. Okay? You're pouring it through your kidneys, so it's in and abnormally going through your kidneys out your urine. You're losing it because there's a problem with your renal system, or you're using it up because you've got something else going on that's using it. Using and losing is an easy way to remember a low albumin. Conditions related to that, okay? For elevation, it's really unusual to have too much albumin. It's more the loss of your albumin. But dehydration, think about what dehydration does. And as we go along, dehydration shows up on a lot of different elements that we test. You haven't really lost your protein, or you haven't really increased production. What have you lost? Water. So your blood volume is lower because you don't have enough serum. You've lost the water component. You still have the same chemicals, and because of that, they appear to be more concentrated, okay, because it's a relative. So these people that are dehydrated, we'll give them fluids, and then our body will kick in and get things straightened out. If you leave the tourniquet on too long, and what is the limitation on tourniquet time? 1 minute, and we know how fast 1 minute goes. But if you leave it on longer than that, this starts to play into it because you are cutting off the blood flow. You're restricting the fluid, so you can get a false elevation. Okay, here's a whole bunch of globulins. Okay, the four main parts, alpha 1, alpha 2, beta, and gamma. And there's a few listed under here. There's several in your textbook, but we're not going to go through all of them, okay? But there are several that you do need to know something about, okay? And a lot of their names have to do with where they are. So we're going to talk about these. The first one in the alpha 1 group is AAT, alpha antitrypsin, okay? Get used to this term, an APR. It's not radio. Acute phase reactant. There are a lot of things that elevate during an acute phase crisis in your body, okay? And this is one of them. Its job and why it would be elevated when you're having an acute phase, or you have something major going on, inflammation, infection, or whatever. I don't know how detailed you got in hemo, but when your segs go to do their job. And what was their main job? They're Pac-Mans. They're going to eat up foreign bodies. As she said, did you hear her? Phagocytosis, macrophages. And they release this component that's listed here, okay? The elastin and collagenase, they're sticky substances, okay? Because they have a job to do. They've got an invader they're trying to get rid of. And this is a sticky substance. And elastin kind of makes you think of something sticky. Well, if you have this an ongoing problem, eventually you've got too much of this elastin, and the AAT, antitrypsin, its job is to get rid of it. Okay? Well, if you have a problem and the next bullet is deficiency, and there is a common genetic deficiency in Caucasians where they don't have enough or any of this, then that elastin builds up in their bodies. And the main problem is in the pulmonary system. It's sticky in the lungs, and it starts creating early onset emphysema. So when you see these people in their 30s and 40s with emphysema, it's probably not because they were big smokers when they were adolescents, okay? They probably have this genetic defect where they're not making enough of the AAT to get rid of the excess elastin. So it has settled in their lungs. It settles everywhere, but in their lungs is where it's creating the main problem. So early onset emphysema is related to deficiency, okay? Alphafetoprotein, AFP, and we will be referring to this again under another part of the textbook later. Fetoprotein. It was first found because it is produced by the fetus. Up to about week 14, 16, it's said to peak at week 13 gestation age. And we use this for fetal maternal screens. So we will collect blood on the mom, and if it is not where it's supposed to be at the 13 weeks, then we can utilize it for indication of problems. After about 16 weeks or so, it starts coming back down. So timing is real critical. You get the mom in there at 13, 14, maybe 15 weeks to get her blood drawn, because after that, it's coming down, and you might get a false indication. Well, there again, 13 weeks, some moms, I just find this hard to believe, but they don't even know they're pregnant. Obviously, they're not going to get any prenatal care, and they don't know about this. So, you know, they might not even see the doctor till, I cannot get rid of this weight, you know. What's this thing sticking out, this little leg sticking out? What's wrong with me? And it's too late. However, we get into morals and ethics, and I'm not going to get into my personal feelings on this, but sometimes I think we know more than we need to know and it creates some problems. But sometimes you can take something and turn it around and make a moral issue out of it, and this is one of those. But in babies with neural tube defects, it goes really high. So at 13, 14 weeks, they measure the mom, and it's really, really high. They consider a neural tube defect, such as spina bifida, you know, where they have a hole in their spine, or excuse me, I'm going to have to cough. And that's where some of the medical field wants to get into terminating your pregnancies. Also, if it's extremely low, it's an indicator for Down syndrome or trisomy 18. Okay, so that's in the fetus. However, later in life, it can come back with certain conditions. Normally, after birth, there's no AFP in the mom or the baby, except in a large percent of hepatocellular cancers. It'll start showing up again. Okay? So if for a reason they're looking for something like that, then they will measure it again. So usually you have two separate lab orders. You'll have the fetal maternal screen for the top portion of this slide, and then you'll have another AFP for your hepatocellular patients. You know, so when you get this, could even be a child or a male, they're looking for different things. It's the same component that we're measuring. With the fetal maternal screen, they give them a whole lot more information. So obviously, you wouldn't want to order that. You might get an answer, but you're going to get a whole lot more information that is not applicable. So you'll have two separate orders for this same component. The next one, I'm going to skip this one, I decided. But as you see, APR here. Haptoglobin. This, now we've moved over to alpha 2, okay? It's also an APR, and it's got an H in it, so that'll help you remember. Its job is to get the free hemoglobin. When your RBCs are disintegrating and the hemoglobin's released, we're a great recycler. We want the iron. So it is preventing loss. If we didn't have the haptoglobin to bind it, it's going to be flushed out of our system. And then eventually we're going to have iron problems. So when we are having intravascular hemolysis, that's a lot of breaking up of the red cells inside your body. That's the only time it's acceptable to have a hemolyzed specimen. This will be low because it's being used up. It can't work fast enough because there's way too much hemoglobin being released. Ceruloplasmin has a C in it. It binds copper, and you guys are thinking, copper? That's a metal. That's what my grandma wears around her wrist to keep the demons away. I don't even know what copper is for. But we need minute amounts of certain metals, and copper is one of them. We don't have to eat it, and I sometimes think we developed it because we ate the dirt outside when we were children that had metals in it, and our body just wants a little bit of it. It is essential, but very little bit of it will become toxic, so we don't need to ingest anymore. We have enough to recycle because of the plasminoplasma, okay? But one condition that I want you to remember is Wilson's disease that's related to copper. Your ceruloplasmin will be low, and your copper is elevated with this condition. And because you have too much copper, because it's not getting bound up, it's going to settle and deposit in certain parts of your body and cause problems, especially with your liver and kidney and your brain. But one place that you can see it, just, you know, they say our eyes are a good determiner of our health. And if you ever go to the optometrist, they look in your eyes and they can see a lot inside. That's like a window to your health. There's a rim right before the whites start of your eyes. You start developing a rim of this excess copper. And you've probably seen some people. It's really pretty, especially if you have blue eyes and you have this little golden circle. It's really pretty. So look up some pictures, Google some pictures so you can see them. Of course, the darker your eyes, my husband has black eyes, and his are darker than yours. They're about like yours, Brenton. They'd be harder to see because it's like a golden, think of copper. You know, it makes that rustiness. That's a little harder to see. But in your really, as my sister-in-law says, pale eyes people, you can really see it distinctively. And it's because this copper is building up toxic levels along with building up in these other organs, creating problems. So you will have low ceruloplasmin levels. And that's the problem. You don't have enough of them to bind the copper, so it builds up into toxic levels. Okay? So sometimes the problem is not that we have too much of something. This is we have too little of the binding protein, which allows what is supposed to be binding to build up. Okay? The next one is macroglobulin, alpha-2 macroglobulin, AMG. It is a protease inhibitor, and we will see it in nephrotic syndrome. Nephrotic syndrome, we see a lot of things happening, and that's where your kidneys are allowing things to go out of the body that it shouldn't. The kidneys are like the liver. That's a big filter and allows certain things to pass, but a lot of things have to stay in. So this one builds up really high because it doesn't pass, while it's allowing, in nephrotic syndrome, it's allowing a lot of other things to pass that shouldn't. Transferrin, and I know these are a lot of different proteins in here, but these are all the ones that we measure and that are significant. But this is all that I want you to really know for right now anyway. Okay, now we moved on to the beta section. Transferrin, what's the word look like? It's going to transport ferrin. Anybody recognize that word from the periodic table? Iron. Okay. It transports iron. It takes it to the storage places. Iron was related to our hemoglobin. Okay, so we have some overlap with these proteins. We use it to monitor iron deficiency anemia. So you may have alluded to us a little bit in hematology when you talked about IDA, iron deficiency anemia. Okay? This is the only one of significance that is reduced in an acute phase reactant. Okay? Almost all the rest of them are elevated when you have an acute phase going on. C-reactive protein, and this is one of the first ones that's going to go up when you have an acute phase reactant. It gets its name from strep pneumo. It precipitated with a C substance from strep pneumo. So it was a C reactant. That's where it got its sophisticated name, and we've just stuck with it. And we use this for coronary vascular disease, CVD, monitoring, or prediction, risk assessment. We don't want very much of it. So the higher it is, the higher your risk, which means you also have inflammation going on. And they have studies now that have linked cardiovascular disease and issues with acute phase reactants. And it has become so important that with our next generation of studies of methodology, we've improved it so we can go better on the low end. Okay, on our biuret methodology, it said 1.0 grams per deciliter was the low end. Well, maybe we decide for some reason we need to know, is it 1.3 or is it 0.5? Then that becomes very significant area, and with our biuret, we can't detect that. We can't give them good answers because our sensitivity is not good enough. So we do more studies, and with newer generations of testing for CPR, VRP, we came up with what we call HS, high sensitivity. And it's on the low end where we can give them more decimal answers. Rather than just saying a 1.0, we can now say it's a 0.65. because that low end is important, can give us a better indicator for cardiac risk assessment. So you may have an older method that just gives you down to a certain number, and it's just called a CRP. But most places now have what they call the HSCRP, meaning it goes pretty low. So the decimals are very globulins. That's the last big gamma globulin. You know that there's 5. Is there more than that now? Since you had a whole semester, they might come up with some new ones. This is all I really want you to know. Okay, you have a whole semester to know all the details, but know them in this order. GAMD, that is the amounts. G, we have most of. And A is next, and M. Minute D and E. So for the most part, they just want to look at G and A and M. Okay, let's talk about high proteins, hyperproteinemia. Well, we said the element that's in a protein that's not in a carb is what? Nitrogen, okay? So it is associated with excess nitrogen. Well, if we take in too much of it, that can create a problem. If we get dehydrated, as we talked about earlier, we were just talking about albumin particularly, but same thing, high protein in general. If we have a lot of the globulins, and in some conditions, well, really any of these others, we could have a lot of, but the alpha-1, alpha-2, and the beta, there's not a lot of them to begin with. Remember, it was 60% albumin, so we've only got 40% for these 4 parts, and the most of them are your globulins, your gamma globulins. Gamma globulins. So when we see increases, for the most part, it's going to be in the globulins, which is going to be your gammas. So if you have an elevated total protein, we measure total protein, we did in our lab. Same way you're going to measure it, only with a piece of fancy equipment in the real lab. We measure albumin, and it could be low. Got a high protein, and the albumin's low. It has to be some globulins, okay? And for the most part, it's in the gammas. We do a calculation here, and I've got another slide for it. You've got a box in your textbook that gives you quite a bit of information about excess proteins. Multiple myeloma is going to be the main one that you're going to hear about and need to understand. They're making way too much of your globulins. And so if you have a decreased protein, hypoproteinemia, same thing, it's affected your nitrogen. Well, you probably have too much volume in your water, or you're not taking in enough, which could be just your diet, or it could be a malabsorption problem. If you get rid of too much water, that's related to nephrotic syndrome. It allows too much stuff, too much liquid in other parts to be eliminated, crossing in the kidneys. Testing, you already know all about biuret, right? What's the wavelength? 6 of you should know this. 540. It's a colorimetric method, and you saw a change from blue to what? Okay, violet. And we can visually see it. We treated it with copper. We got to have some peptide bonds. You know, if we got amino acids but no peptide bonds, we don't have proteins. Okay. Some other methods. This biuret's only good for serum. Urine, we usually don't have protein. We're not supposed to really have any. So when we start having it, it's going to be in small amounts. The protein in the serum was what kind of units? Grams. Grams is big. That's one of the biggest units of anything that we have in our body that we measure. When you get it in the urine, we're talking about micrograms and then milligrams. Okay, so we can't use the biuret. It only went down to 1.0 grams. So we have use a refractometer or a chemical strip with a color reaction that we can see based on pHs. That we won't get into that method, but just think of it as a chemical strip on urine. Well, we can also measure protein in other parts of the body and other fluids such as your spinal fluid, which we do. You do have a small amount of protein in your spinal fluid. You can't use the biuret because it's in milligrams. So we have some other methods using turbidimetric. Sulfosalicylic acid, which we can also use on urine, and trichloroacetic, it's used on urine too. So on your chemistry analyzer, you're going to have a biuret that's only for your serum, grams. Then you're going to have another protein for your spinal fluid. We called it CFP, spinal fluid protein, and it was in milligrams, and it was an SSA or something like that. And that same methodology can then be adjusted for urines for milligram measurement. So you might have 3 different proteins on this one chemistry analyzer. And make sure you understand the difference. Of course, we're barcoded, so you might not even have to know that, but when your computer goes down, you definitely have to know that. Just know what biuret is doing. We are making an alkaline pH. This sodium tartrate keeps the copper from precipitating out. The copper is what's actually reacting. Okay, the AG ratio, albumin over globulin. I told you we'll measure total protein, and then we will also measure albumin. They're really cheap tests. They get done on almost all panels, but we don't measure all the globulins unless they are specifically looking for one of them. So just a real quick calculation. Our computers do it for us, and it helps the physicians look at the multiple myeloma. I said you're going to have an elevated total protein, a decreased albumin, and an elevated globulins. We do a real quick calculation of albumin over globulin. So just think about how you would do it. You've got a total protein, you've got an albumin, and that's it. How are you going to do this math? You have a total protein of 6.0 and an albumin of 3.5. Anybody give me an AG ratio? If I subtract albumin from total protein, what's left? Globulins, okay? So my globulins would be, thank you. So what's my AG ratio? AG. And albumin was 60% normally. So normally it should be well over 1.0. Okay, albumin should be well over half. So normally it should be well over 1.0, okay? So by just a quick little math, they can say, oh, one or the other is out of kilter. So your report will have total protein, albumin, AG ratio. The methodology for albumin, which we're not going to do, This is colorimetric. You got to have something with color. Bromocresol green or purple are the most common ones, but we do some other colors, oranges and such. But do know these: bromocresol, purple for albumin. And these are the reference ranges that I want you to know. Okay? And note, under the total protein, we have a lot of bedridden patients that we are monitoring on a regular basis, our nursing home or rehab type patients. Because they're bedridden, they have a reduced total protein all the time. This stands for spinal, that's not spinal protein. I think that's supposed to be CFP. Cerebrospinal protein. See, it's in milligrams as opposed to grams. This is 6,000 milligrams in your serum as opposed to 15 milligrams. And just know the quantity of your GAMDs in relation to each other. Here is a nice scan showing you some electrophoresis, and right here, here's your beta. Normally it comes down, makes your valley, and comes back in for your gamma. Well, there's this area here, it's called a beta-gamma bridge, and you will see that in cirrhosis. So we can't distinguish where the beta stops and the gamma starts. And that's a telltale diagnostic indicator for cirrhosis. And